Hi, here we are discussing about a project design and analysis of reversible approximate full adder and its applications with the optimized 4:2, 5:2 and 7:2 compressors for efficient approximate multiplier. Here the approximate and reversible computing are increasingly used in low power signal processing, medical imaging and machine learning applications where small inaccuracies can be accepted to achieve a reductions in power, area and delay. So this method offers more advantages such as a lower switching activity, reductions in heat dissipations in approximate method, but they also faces certain limitations including error accumulations and the need for efficient alternative structures. Thus in this work using a reversible gate structures too. So here the existing reversible approximate full adders have a lot of designs, but it will present with a more error analysis. So this project aims to design error directions in reversible approximate full adder with a lower cost and controlled error behavior. So for that this work presents with a new approximate full adders which using only the praise gate and one Feynman gate is introduced to reduce the number of reversible gate and a constant input and garbage output. So while conforming the approximations to least portable input combinations to avoid a major error propagations. The existing examples of RAFA1 and RAFA2 based reversible adder designs are used for comparisons to highlight the improvement in the logic size and error rate. So additionally, this designs also developed a proposed adder to build reversible 4:2, 5:2, 7:2 compressors and an approximate multiplier architecture, allowing evaluations of how the new full adder behaves inside the higher order arithmetic blocks. The entire designs in this work is described in Verilog HDL, functionally verified with using a model sum and synthesized on Xilinx FPGA to measure LUT usages and slice registers, delay and overall hardware efficiency. So for this analysis of this approximate multiplier which is using approximate full adder, so we have used some reference paper. So these are the reference papers: 8-bit approximate multiplier using approximate full adders, and so this one, the design and implementations of approximate multiplier using approximate 4:2 compressor, and this one is a reversible full and half adders with the optimum power dissipation, and this one an approximate low power lifting scheme using reversible logic. Okay, so here this one we consider as the existing method. This paper already they proved the reversible logic full adders which using two designs. One is a RAFA1 and RAFA2. Okay, so here RAFA1 it contains a 3 Feynman gate. Okay, but it will be take more logic sizes. Okay, so additionally they will be offered with go outputs and sum and carry outputs. Okay, so further they reduce this RAFA1 to RAFA2. Okay, they used only the 2 Feynman gate. Okay, but what is the problem means here this RAFA2 and RAFA1 it will come with a more error analysis. Okay, so error it will be take. Okay, so further we need to reduce this errors, but we need a new novelty reversible logic gate. Okay, so for the purpose this proposed work we introduced a praise gate and Feynman gate based architectures. Okay, so here the praise gate means here you can analyze the design of the praise gate. Okay, so it will become with the P, Q, R. Okay, so the Q value it will be XOR the output and R value it will be AND the output. Okay, so why? Because if you are given a C equal to 0, Q equal to come with a XOR gate and R equal to come with a AND gate, so which means it will be work as a half adder. Okay, so and additionally we used one Feynman gate. Okay, so this one. Okay, so it will be come with a one XOR gate. Okay, so we interconnect this to logic gate, so it will be come with a very less logic size and very less error compared to the previous designs. Okay, so now we can analyze the coding part. Okay, so here this is the exact method. This exact method additionally we design this concept which using this full adders. Okay, reversible full adder to design a 5:2 compressor, 7:2 compressors and 4:2 compressor method. Already the full adder is one of the compressor, that is a 3:2 compressor. Okay, so using this all compressors we design one novelty architecture of the multiplier. Okay, so that multipliers we have integrated here. Okay, so this is the exact multiplier architecture. So exact 7:2 compressor, 5:2 compressor, 4:2 compressor, full adders and half adders, it will be used in this architecture. And this simulations it will be run, okay, with a zero error. Okay, so here you can analyze the error. Okay, so zero errors. And this designs we compared with the proposed architecture. Okay, so this is a proposed architecture. It's also developed with the 4:2, 5:2, 7:2 compressors. Okay, and this is our proposed architecture simulation part. Okay, so here we marked with a red cursor. Okay, so compared to the exact method, so 101 into 18, it will be come with the 1818 value. It will be come with zero error. Okay, but in the proposed it will be occupied only 128 in the error cases. Okay, so some of the output the proposed architectures it will be given zero error also. Okay, you can analyze anywhere. Okay, so here it's 0, here it's 0, here also it's come with a zero error. Okay, so it's mostly working as accurate and as well as approximate part. Okay, so here further analysis, here 101 and cross 18, it will become with a 1818 is a original value, and 1690 it will be produced in the proposed architecture. Okay, so the error equal to 128. Okay, so further this work we compared with the RAFA1 and RAFA2, right? So here RAFA1 it will be occupied with the error means, so same 101 cross 18 means it will become with the error 11784. Okay, so totally it will be take more error compared to the original designs. Okay, so here this one is a RAFA2, it's also come with a more error. Okay, so 1216, that is the error area. Okay, so further we reduce the errors in the proposed architectures and we proved it with a less error analysis using the reversible logic full adder design. Okay, and this works also synthesized in Xilinx Vertex 5 FPGA. Okay, here the exist method it will be come with a 216 LUT and 75 occupied slices, IOB equal to 32, and synthesis report we can analyze the delay. Okay, 27.563 nanoseconds. So here the proposed architectures it will be come with very less number of LUT, so 61, and occupied slices equal to 30 and IOB equal to 32, and this one is RFA1. Okay, 225 LUT and occupied slices equal to 201, and this one is a 76 LUT, so RAFA2 76 LUT and occupied slices equal to 28. Okay, if required you can use this RAFA1 RAFA2, otherwise you can take only the exact method and the proposed full adder method only for your comparisons. Okay, and we have written a comparisons document also for this work. So the initial comparisons we have designed with the number of reversible logic gate. So here the full adders folders it will be available with all the reversible logic gate. So what are the reversible means? Fredkin, Feynman gate, FG, TG, FRG full adder, and RAFA1, RAFA2 and HNG gate, Priest gate, proposed full adder, SCG full adder, TOEFL Feynman full adder, TSG gate full adders. Okay, and these all full adders we have synthesized and it will be compared. Okay, so this is a comparisons table. Okay, so here you can analyze this is our proposed full adders. So here this one is a truth table, so you can analyze one full adders RAFA2, RAFA1. Okay, so here you can analyze the approximations part. Okay, so this 3 is a approximations one and this one is a exact method. Okay, and this is the comparisons for the multiplications, exact multiplier, proposed approximate multiplier, RAFA1 and RAFA2 multiplier. And next we have written abstract document for this project, title, base paper abstract, improvement of the project, advantages, disadvantages, existing works. Okay, and related notes for this project. Okay, and finally come up with the literature survey and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.